So just 4 or 5 days.
5 days, yeah, we got a week.
5 days.
Spring break used to be 2 weeks, but then when they added a winter term, they expanded the winter term, the winter break, because they needed a 4-week term, and so then they cut it down to 1 week. So we have a 1 week spring break, so that way you can get out around the same time, the beginning of May, essentially. So, but yeah, we get 2 months to go, right? As of this coming, you basically have, well, this week we only have about, was it 7 weeks of classes? We're about halfway done the semester, so we're halfway through, depending on your perspective. So. All right, let's get started. So here's another example. So we were doing block diagram math, and as we mentioned, it's pretty helpful if you can't remember to have these elements up when you're doing these, because if you're looking for something to kind of provide a guide, just using this will help you see the algebra that needs to be done, and then also pictorially what you're trying to do. And I did update the slide, so this should be the latest and greatest. Anybody check to see? No?
You updated.
I updated it so that this should be included in the current slides. So, all right, so now we have another example. Okay. So this one's not too bad, because if we look at it, we have a bunch of feedback paths that are all sort of enveloped around each other. So you can sort of do a multi-step process. You can combine this one, then you can combine this one, and then lastly, you can combine that outer, sort of the biggest one. Because you can't combine the outer one first, because again, you would lose information about what's the feed forward and what's the feedback path. So in this feedback loop here, we see that when we combine it, that this gain becomes the feed forward gain, correct? Once we combine those all into an equivalent block, we have something that has our summing junction, and then that's just a simple feed forward block. So another reason why you can't just combine them in any order you want, because this feedback element here, this gain, gets incorporated into the feed forward block once you combine them. So let's erase all those.
With each 1, 2, 3, always it's the same feedback, just sort of at the top.
Say that again?
With each 1, 2, and 3 all be the same. It's the same. It's coming from the same block or point.
Well, so the input definitely is C. Is that what you mean? But the thing is, what comes back over here is C times H, right? H1. What comes back over here is C times H2. And on and on and on and on and on. Oop, I gotta erase that. So this is just combining them all in one fell swoop. We have that feed forward back, and then we just sum them all together. H1, H2, H3, and you'll notice negative, whoops. We have negative, positive, negative. Those three can be combined into one single feedback block. And then these two, which are in cascade, can be combined in a single block. So now we end up with H1 minus H2 plus H3. Why is it minus H2? Because if you look over here, it's plus, isn't it? So is that a mistake? Yeah, if you look, let me erase all this. If you look over here, minus plus minus, but the minus is over here. So minus H1, when I move the minus in here, plus H2, minus H3. You could have made this a plus if you wanted to, and then this becomes, right? It just takes the negative of the signs. So you can go either way. The only reason why I included it with a negative is because most of the time we're going to have a feedback path that's going to be a negative feedback. All right. So that's why we would typically show it going negative as shown. So now we just have a simple feedback path plus input gain. And that's what we have. This right here is G over 1 plus GH. It is the equivalent of this block all combined. The G1 up front is where we put it in cascade. Okay? Questions on that?
And then, because we really don't use yeah, on this one, I combine Q1, Q3, H1, then combine again. That,
If you do them one at a time,
yeah,
yeah, it would take you a little bit more time, but you'd still end up with the same result if you did them one at a time. Okay, this one's a little harder. Right? What's that?
no,
Okay. Because we have a pickoff point here that is kind of living inside that feedback path. You can see the G2H2 feedback. So that makes it difficult. That's probably the only difficult part about this is if we can move that feedback, that point out of there, then we can maybe combine these elements here, and then somehow, figure out how to combine that element over there. So let me erase the slide because they just keep writing on each other. So what would you do? What would you recommend? Can go back up to the table. Guess the fastest way to do it is to do it this way. Which one would you recommend? Here's the table. Let me do this. Hold on, let me just let me clear all this. Oh, this is that I want the whiteboard. I'll just paste it in like this. Once it logs in. Okay, so go back to my presentation. Go back down to here. Which one of those do you think is most useful? So here's our image. And here is the sort of the table to make things easier. Which would you choose? 1, 2, 3, 4, 5, 6, and why? Four?
Yeah.
So you're moving a pickoff point ahead of a block?
Yeah.
Okay.
Yeah, that got point ahead of G2.
This pickup point right here. How come it's not writing? Oh, there we go.
Yeah, there, I would go to the board, that got point.
So are you moving it ahead or are you moving it behind?
It's going to be moving ahead with the order of the board.
Let's look over here. So item number 4, moving ahead moves it to the left, right?
Gotcha, I got the wrong location, yeah, so moving behind.
So you would move that over here. Do you have any issue with something that looks like this? That's essentially what you would have, right?
Yeah.
You're moving the same point and you're putting it into the summing junction. You could put a 1. So you could put a block here of 1.
You'd have to
But
multiply by
I guess the
G2
question
still.
is, why would you need that one there? It's plus, it's adding it to itself, right? Or would you double it? Two of them together, 1 + 1 is 2, right?
Oh, you'd still need to multiply that by
hold
G2
on.
though.
We can barely hear you. I don't know why. Can you speak up again, Drew?
Yeah, can you hear me?
I'm having a hard time hearing you. Hold on. Let's see if I can make it so that we can hear you. Now?
Hold on, can you hear me now?
Keep going, keep talking.
Can you hear me?
Yeah, I can hear you. For some reason, the speakers
Alright.
here are not plugged in. So go ahead.
Gotcha. When you have to multiply by G2, when you add it back in anyways, so you wouldn't be just adding the same point to itself.
So you could be multiplying it by G2. So Drew brings up a good point.
You have to because you moved it, right?
Right. Because if you moved it to the right, so you're moving a pickup point behind, then you'd have to include the G2 here. Well, let's see what I did. Exactly that. Okay. So you don't multiply it, Drew, by G2, you divide by G2, because over here, what comes out over here is V3, correct? So this now would go into this block, and if I want that to be the same, then I have to divide by G2.
Yep.
So now I can combine this pretty easily. This is a feed forward, right? This is just adding it together, so that's not a big deal. What is the block diagram of this? How would you have that block diagram? Or what would you replace it with? 1 minus or plus? Correct. That's what that block diagram becomes. Excuse me. And then you would add, once you've done these, you got to do a feedback path here and on and on and on. So let me erase it. There you go. Okay. See how those are combined? Then we can cascade them. And we can continue there. So now we can put these in cascade. We do this inner loop. And now we just have a simple feedback path. So here's our final result. Questions on that? Feel okay? So this here is the transfer function relating C to R. And it is the closed loop transfer function. Why is it closed loop? Because this here is closing the loop. I bring that output, somehow I bring the output all the way back to the input. So you close the loop. If you had an open loop system, you basically stop the feedback path. So there's no connection over here. That connection is open. And so we'll talk more about closed loop gain and open loop gain as we move forward when we look at some of the material. All right, what do we do about this one? How about we spend 5 minutes? You can try this one. So give you 5 minutes. Oh,
So they're not like it's one of this big, but they just like sitting.
no, they're actual S values.
Oh, wow.
So try this one, see if you can get, or what you would get here. That way I won't keep writing on the slide and having to erase it. Okay, let's do one more minute. One more minute. All right. Suggestions. How should I tackle this problem? Or we tackle it? Let's do it together. Even Jude is joining in to help us out. She knows it's an overwhelming task for just the 5 of us. So, well, 6 or 7, including TV land.
And, as.
Yep. So this becomes S squared, right? And you can combine these into one block. Once you have that, then you can see that that block is going to be a block, a part of a feedback path. But the problem is, what's the feedback? There is no S term in here. So is it really a feedback? Everybody understand what I'm saying? Which is here's your summing junction. And this block inside here, we said is S squared plus 1 over S, right? Now we come, and we've already got rid of our summing junction. But the problem is we have this, right? So is that really feedback? Why isn't it feedback? Can't the gain just be equal to 1? So I can actually get cute, and I can put a block if it throws you for a loop, and I can actually say, and we can make it look like we've always made it look by going underneath. Isn't that exactly what we have? It's the gain of 1. That's all. So once we have that, then we cascade it with this. And then we have a feedback path that we're more comfortable with that. And we have our answer. So here's the combination. And this is where it might make sense to do a little bit of math, right? So if you have fractions and they're not combined like this, you have an S squared plus 1 over S. It's better to put it under a common denominator now because it just simplifies your math. Now we're going to go ahead and do that unity feedback path, or can we just move it over here? There's no advantage to doing this. This just shows you that there's another way to do it, because now we can take these two, and what can we do? We can combine those into a block that is 2S. And so what Barzilay pointed out earlier, or maybe even Pat, was it is less work, right? To do one less feedback path. So if you see this as a feedback path, you actually have a little less work to do. Because now these are these two are in cascade with one feedback path. And that's almost your final answer. But it's ugly. So we want to get this. Let's go back over to here and see if we get the same result. So let's put this in a feedback path, right? So we have G. Let's just check to see if the results are the same. Over 1 plus GH. And that's going to be equal to S cubed plus 1 over S plus S cubed plus 1, right? When we combine it like that. So this is the block that we end up over here. This is that block. Now we have a 1 over S. And this is our feedback block, S. Right? So now I'm going to cascade that. So I'll put it in cascade. So I have S cubed plus 1 over S to the 4th plus S squared plus S is the feed forward. And now I only have that feedback path. So my overall system, S cubed plus 1 over S to the 4th plus S squared plus S all over, because I'm still here. I got to close that loop. So it's 1 plus S to the 4th plus S squared, plus S, sorry, not S squared. All over. Now I got to do common denominator. So let's do it up over here. Sorry, I'm running out of space. And what I end up having is S cubed plus 1 all over 2S to the 4th plus S squared plus 2S, if I've done that correctly. So that should be our final answer. Let's check and see. Is that what we have? Yes, we do have that, because this, when you expand it out, this becomes 2S to the 4th. This becomes 2S, and you have your S squared. So it's the same thing. Just looks a little bit different. So you could do that either way, whatever work you find easier. So sometimes looking at this and being able to say, hey, if I can move things around a little bit, I might save myself a little bit of work. Maybe not, maybe so. It's totally up to you. Okay, so let's finish up this chapter with some forms and some characteristic equation. So we're going to simplify our future analysis by trying to simplify these block diagrams as much as possible. Normally, what we're looking for is the characteristic equation. And when we have this characteristic equation, we can assess a lot of different things. In our characteristic equation, we can have what's called a canonical form. Sorry for the terms. This is just what control systems engineers use in math concepts. So we're going to talk about it in terms of unity feedback and non-unity feedback. Non-unity feedback means H of S does not equal 1. Okay, it's a number. A unity feedback system is one where H equals 1. And when you look at either, there are some analyses when we do root locus plots, sometimes it's easier to actually have a unity gain feedback system do its analysis. But you can always go back to having a unity gain system. I could even do that over here. I can make this system unity gain by, how would I make this unity gain? What I'd have to do is I'd have to incorporate this 2S somehow back in here. Okay, we won't worry about that now. We'll just see how, that's just a standard representation of the form. And as we talked about, the feed forward gain is G and the feedback gain is H. So our closed loop gain is going to be G over 1 plus GH. We've done that a zillion times, and that's only for negative feedback. If our open loop gain, here's what we talked about earlier, where we're going to pull back that input to our summing junction, and we're going to open loop it. And look what happens. The open loop gain is the gain between the input here and to this point here. Okay, it's not what the output is. So if you had to do another term, let's call this FB of S. open loop gain is going to be equal to the feedback of S divided by R of S. Okay, and the way that we solve for that, so our feedback of S, that's going to be equal to our input. Okay, then we go through this G, so it's going to be times G of S. And then that comes back over here, and we multiply that times H of S. We're not adding or subtracting anything because we're stopping right at this point. My feedback exists just at that point. Okay, so I don't subtract anything. So if I do my open loop gain, it's just G times H. Okay. So one of the things when we look at Bode plots is we want to look at this open loop gain concept and see, do we have an open loop gain that is going to potentially cause us to have a phase shift that's going to result in an unstable system. So that's when I say this is used to determine if your feedback becomes positive. How can your feedback become positive? It's a negative number here, so shouldn't it be always subtracted? How can a negative number become a positive number? The gain is also negative. How does the gain become negative? Let's just assume that both of these numbers are going to be positive, right? It's going to be some positive number. How do we end up with a negative gain? Or a negative feedback, I should say. This is a tricky question. I can pick on a lot of you in this class because you're in 321 with me. If I have a vector over here, how do I make that vector go up here? What's that? Yeah, you phase shift it by 180 degrees. So if I have a sine wave or a cosine wave input, sine of omega t in the time domain, these here, remember S is complex frequency, right? It's J times omega. So it's possible that when I do my calculation, my gain could have a magnitude and an angle. Could be a complex number. It definitely will be a complex number, right? Because we have the J term. And so depending what my frequency is, this theta can become a negative theta. The negative theta and the negative here become a positive number. So if you introduce enough phase shift in a system, you actually can make your negative feedback system become positive feedback. Anybody here in the audio? Bandpass filters. What's a bandpass filter? You block out frequencies above and below a certain range. And that center point of that range is usually called the resonant frequency, where the impedance is really, really low. So it doesn't really filter that out. That's kind of what you're doing there, is anything that's above and below those points, you're trying to make sure that the phase shift is such that those things just get subtracted away. But when you're trying to do resonance, you want to amplify it so you actually have positive feedback at those specific frequencies. So you can actually, we actually use this practically all the time. Also, we talked about crystal oscillators. When we're trying to operate just at a very specific frequency, we would want the feedback to be positive so that the resonance just continues to perpetuate itself. This will make a lot more sense when we look at Bode plots. And I'm assuming you've all done frequency analysis and John's, if you've had John's 342 class, I think is when you, what's that? Oh, good, okay. When you get done with this class, it's math, but you'll see how the Bode plots, because a lot of it, he talks about a cutoff frequency and stay 3 dB above and below. We'll actually show the math as to why it is and make it hopefully crystal clear and how easy Bode plots are. It's just a really simple math extension from that, from Laplace. I think this is our last slide, which is the characteristic equation. So the characteristic equation is it characterizes the system output. So what is the system output going to be most responsive to? It's the transient analysis. So we have a natural response and a forced response. The forced response is going to be whatever it's going to be. We have no control over that because that's what the input dictates it to. But the natural response is what system we design and then how it responds to that. So the characteristic equation characterizes or describes the behavior, the transient behavior of the system. So that's why we describe it as a characteristic equation, because it is really important to us. Because once we know what the characteristic equation is, then we can actually say, is the system stable? Is it not? How long is it going to reach steady state, et cetera, et cetera. Remember all those second order system equations, rise time, settling time, peak time. That was all based on the system and its natural response, not on the input. Okay. Any questions on block diagram map? Because you now have a homework assigned. I think that was homework 5, if I'm correct.
We're at 5 or 6.
6 has not been assigned, right? You can't see it. You can see homework 6. The actual problem. I thought I made it so that it wasn't. Oh, that's okay. I thought I made it inaccessible, but I think maybe I made it accessible because we might start on the homework today. So
You made the solutions. I saw a notification like homework 6, we were late on homeworks already. But
Well, I think, that homework 5 was some full zero maps and like overshoot.
okay, so homework 6 is the block diagram stuff. So yes, that's the one that's available. Homework 5 is due today, right?
tomorrow.
No, Thursday. Yeah,
Today.
yeah. So that the block diagram stuff is due next week, right before break. I know it's a pain, but this way you don't have to worry about it over break. Okay. And the homework solutions should be available right after class. Yeah. So I made it that way. And then homework 6 will be available right when that's due. So trying to get ahead of it. So any questions on block diagram stuff? We can look at the homework real quick. I guess I closed it. I don't know if it still might be here. No, I must have closed it. So let's see. So number 1's fairly simple. Number 2, you got to do a little bit of work, right? To move something, you have to move a pickoff point in one direction or the other. And if you move it, you should only have to move one point. And then over here is now I want you to plot the unit step response. So how would you tackle this one? I don't know why the summing junction didn't get printed properly. But what is the unit step response here? How do you plot that?
Would you want to add?
Well, you can't add it together, right? Because it's a feedback. So you got to do a little bit of math to make it work. And then how do you plot it? There's 2 ways you can do it. What would you do?
Solve for the full zeros.
You gotta simplify it a little bit. That's step 1.
Yeah.
But then step 2 is the actual plotting process. So how do you want to tackle this problem? You can do it 2 ways. Finding the roots. That's a pole 0 map, but does that tell me what the response is? Response is the time domain response, right? Multiplied by an input, yeah, a unit step. And then what? The pole 0 map usually is only done for the system, the actual system itself. So I don't do a pole 0 map with an input. I just do it for the system.
Yeah.
So you're welcome to do the pole 0 map with the system, but you don't necessarily need to include the input.
Your final value here in the different step inputs and then plot the output.
So the response is, can you do the final value theorem? And the answer is no. Because if you did the final value theorem, that only gives you 1 point. It gives you the final value. I want the response.
Where, what they,
Yeah,
right about.
do partial fraction expansion. Right? That's one way. What's the other way?
Can we just use the simulator?
Yeah, you can use Simulink. You can put this directly in Simulink and plot it that way. That's what you said?
Yes, that's right. We can maybe have it.
Oh, yeah, you can do it in Simulink too, either one.
Yeah.
You may want to try to do it with doing a partial fraction expansion because that helps you understand the whole process.
But yeah, I mean.
You could put this directly into Simulink, yes. That's an option. But then I have a bunch of additional practice problems too, because I know some of these can be really challenging. So you can take a look. And then I also hark back to some previous stuff because I want you to do a little block diagram math and I want to see the applicability of it. So now you're going to have to do some design. So some values of K. So this one is you got to pick the value of K that results in settling time and a peak time that give you less than a 10% overshoot. Okay. So you really only have to pick the value of K that has less than a 10% overshoot. Then you can determine T sub P and T sub S. So evolving it a little bit to say, here's our block diagram and go from there. Okay. Doable. Highly suggest you do the practice problems on that. They will take some time, but time is all you have, right? You wish you had more time, don't we all?
More time. Play more time, wishing for more time.
Yes, if you always wish for more time, then you'll use your time wishing for more time. So try not to wish for more time, unless you really want more time. All right. Oh, why'd that do that? That wasn't weird. Okay, I'm going to totally throw you all for a loop. You have calculators. You have MATLAB. Why would I do any work and introduce you to this topic called Ruth Hurwitz? That the whole purpose of Ruth Hurwitz is to find if there are any holes in the left-hand half plane. Running out of topics to teach? Stable, but if you have any poles in the left-hand half plane, can't I just use MATLAB or your calculator to do it?
Yeah, true, yeah.
If I give you a characteristic equation, what would you do? Stick it in MATLAB and give me the roots. And then you'd say stable or unstable.
Yep.
Yep, right?
Yeah.
There's one problem with that. You all graduating soon and will become what? Engineers. Would you think that I would pay you $85,000 a year to give you a characteristic equation that you just enter in your MATLAB or your calculator and give me the roots and tell me if it's stable or not? But couldn't I teach somebody pretty easily how to do that? Is that really having an in-depth understanding of material? Probably not so much, right? Remember, we have to think about the reason why people have jobs for what they do. In a lot of cases, it's because you have a skill set and you've been trained to be able to do that job. If a lot of people can do that job, then that means there's more supply for that type of job. So they can suppress the pay, not because they're trying to be mean, but it's supply and demand. If I can pay you $15 an hour to do something, I'll pay you $15 an hour. I'm not going to pay you $100 an hour to do something if I can pay somebody else $15 who can do a competent job. But so you can say, hey, wait a minute. Well, how will I get a higher pay as I evolve in my career? Why do you think you get higher pay as you evolve in career? It's not because companies are nice and, I mean, they are nice, but, and they want you to, continue to grow. But the reason why you get paid more over your career, it's not because you're doing the same thing over and over again. You're doing different things. You're getting into higher level design. You need less supervision. You can do it more, you can do more work. You can do it more efficiently. So it doesn't take you as long to do it. So one of the things to think about in your career is continuous improvement, right? That's one of the things in all engineers, you should be learning the continuous improvement process, which is how do I get better at doing that thing? Because if I learn something and I know how to do it really well, in 2, 4, 5, whatever years or months, I could be replaced by somebody who's a lot cheaper than me, or I have to keep my salary at a lower value to entice people to keep me employed. So your purpose of your career is to keep evolving it so that you become more valuable. And when you're more valuable, you get compensated more. Okay. So the reason why I'm talking about it here from stability is I don't necessarily have a characteristic equation that I could put into my calculator. Remember the homework problem here? If I knew what the value of K was, right? Then I could just put that in a characteristic equation and then I can tell you if it's a stable system or not. But you as the engineer have to design a value of K. You have to pick a value of K that's going to work to meet the design criteria. Oh, and by the way, it has to be a real world system. So you have to figure out what linkage or what piece of equipment is going to give you that specific value of K that we see right here. Okay. So that's the reason why we cover this material. It's going to look a little weird at first saying, why do I need to do it? But the reason why we need to do it is because we're going to actually have characteristic equations with variables that we're going to define ranges of what they need to be stable or not. So Ruth Hurwitz is really a design tool. It used to be because MATLAB and calculators weren't really around that do this. You actually had to figure out if the system is stable. Now we don't use it to check stability anymore. We just check it to use for design. What's that?
If you have a correct way, then which they get paid for. If you have to be the calculator and find the answer, it's easy, but the mathematics is complex. So you might have to come up all those indicators from the make us mathematics. Really smart.
Well, yes, there are cases like that where you're given an assignment or a task that is so simple. And when you looked at it, you said, oh, it's going to cost $10,000 to do it, but you did it for an hour. Hopefully, there's some ethics involved, which is if I can do something for an hour, if you have a good client relationship, you'll say, I'll do that for free. It's going to take me an hour. I'll give you the information. And so that's about maintaining client relationships or friendships, right? Which I'll help a friend out moving some furniture this weekend for 2 hours, and I'll help that person out because I want to maintain the friendship. That's just the reality of it is. But if you thought it was going to be a lot more and it's a lot less, then maybe perhaps what you do is it's much easier, but obviously the client didn't understand or didn't know. So what you need to do is maybe provide more description or more discussion in terms of what that process is. So you're not making it more complicated. You're just providing enough information so that the client has learned what you know and how it's a pretty simple, easy process to do it. And then they want that information. And in some cases, clients will ask you to do something because they're too busy to do it themselves. I tell the story every once in a while. I was on loan to a company in Baltimore. So I was living in Baltimore and it was 5 o'clock on a Friday night. Everybody had gone home but me, and I was walking out the door and my boss was sitting there in front of the photocopier at 5 o'clock at night. So I said, hey, what's going on? That's not typical because I was usually the last one to leave. And he said, yeah, I got to get these copies out because I got to get them to FedEx by 8 o'clock because that's when they would ship them out. And that's when this project was due. And so I said, do you want some help? And he looked at me and he said, that would be great. Thank you. So put my briefcase down. And that guy was willing to, I was billing out at $100 and something an hour. That guy was willing to pay my company that I was at the time over $100 an hour for me to sit there and just press copy, print, collate, all that stuff. So you could have gotten somebody for $10 an hour to do it. But the thing is, in that moment, he had a need and he was willing to pay whatever. And he was happy to pay whatever the going rate was because it meant that he could have gotten out of work an hour early. So it really is about that, that relationship. But again, it's what people need. If they have a crisis and you're trying to help them out and get through things, that's when you provide a lot of value added. So sometimes just being around and being available will be helpful. That's the other advantage of working in the office versus working out of your house. Ever heard the expression out of sight is out of mind? Right? So there is advantages to working in an office, especially when you're younger in your career and you're just getting on track. You want to be in front of people so people have that recognition of you. Because if you don't have that, again, out of sight is out of mind, and it's hard to develop that skill set. But I understand because, there are times when I have to work out of my house or something like that. Like I teach the Monday afternoon lab for EET325. I teach that from home. I have enough of a break to go between labs. And it just makes it more convenient so that when I'm done with my lab, I'm home. I just don't have to worry about traffic and all that stuff. So it just is one of those things that you do. So don't make it more complicated, provide value added to the client. And you get to figure out what that is. All right, so what does this say right here? Well, reasonable inputs and initial conditions will lead to unbounded. This is Bible stability. If the input is bounded and the output is bounded, then it's Bible stable. And we've modified that a little bit, which is will reasonable inputs. Okay. Will something realistic be able to do that? Because obviously, if we use the example where water is splashing out of a tank, not necessarily a good thing. So we have two functions for our response. We have a zero input response. This is what we get from our transfer function. And then we also have one that's due to these initial conditions. So if you have initial conditions, like if your tank is 95% full, and you want to increase the flow in the tank another 20%, that could result in an unstable system. So your output, you can't just include, whether the fact that whatever the input is. If you have some way of characterizing those initial conditions, you need to include them in there. But you'll notice that is completely separate from our feedback system or our feedback response. So again, we're going to focus on Bible stability. Here's our zero source response, ZSR, that's what that stands for. And ZIR is the zero input response. So what you're saying is if I have no input, okay, that's the zero source, zero source response. If I have no input, then that's my initial condition one. So that's just the terminology there. All right, math people, what is this symbol? Capital P or pi? What's that? What is it? Seen it somewhere? That doesn't do much. Using your hands doing this.
I know.
Just the product. You've seen this one, the summation, right? It's the sum. It's just the product. So if you have a lot of things that are multiplying together, you can use the product. It's just a mathematical expression. And we know from doing poles and zeros of a system, when we factor them down, we have a bunch of zeros multiplied together and a bunch of poles that are multiplied together. But notice right here, what is this one? Why does that one look different? You should be pretty comfortable with this one by now. Yeah, this is complex poles, right? We do not want to factor down, and we saw this on the test, S plus 2 plus 5J, S plus 2 minus 5J, right? Because we can't go back and bring those into the time domain. We're not going to get a time response out of that. So if we ever have complex poles, we kind of leave those in our standard form, S minus alpha squared plus omega squared. So those are our poles and our zeros. And then if we take those back into the time domain, doing partial fraction expansion, we're going to have our poles that convert to e to the minus something multiplied by a constant. And then our complex poles are going to have my exponential decay. I'll have my radiant frequency. And don't forget, those are now going to be complex, right? So that means that they have a magnitude and an angle. So that we put in a sign. And then also we have to keep in mind, because what we did was omega over s plus alpha squared plus omega squared. We had a constant out front over here when we did partial fraction expansion. We always had to multiply by that k term or divide by the omega term. So this term right here is if we have a non, if it's a number other than 1. So that's essentially what the equivalent magnitude would be, factoring out what the omega. That's why it's not written as magnitude at k at an angle of theta k. Does everybody understand that? It's fairly important. I'm trying to be consistent here that we see that that's not the magnitude. So this gamma k is the magnitude of k divided by omega k. Okay, you can't just pull that directly when you do your partial fraction expansion. Okay, so here's the key. If all these numbers, the real parts here, if all of these are negative, then that means all the real parts, right? Because this is the real axis, this is real. This is the minus real axis. So if all of those are negative, then we have a stable system. Because what was the definition of bibostability when we looked at pole zero maps? What was the rule? All poles must live in the left-hand half plane for a stable system. So that's what we're saying over here. All the poles have to be in left-hand half plane, which means that P sub j and alpha k have to be greater than 0, right? So when you do here, these numbers have to be positive numbers, right? AK and PJ all have to be positive numbers, because these are the actual, these aren't the roots, right? These are the actual numbers. So we can see that the pole is minus PJ. The real part of the pole here is minus alpha k. So alpha k and PJ have to be positive numbers. So don't include the j omega axis because we said that is a marginally stable system. All right. Here's our first example. Is the system bibostable? Can you tell?
Yeah. Wait, yeah. It was,
Why is it bibostable?
so the materials are, that's one that we do.
Wow, look how good he is. He did it all in his head. This is a pretty easy one, right? Our characteristic equation, which is our denominator term, we can do the quadratic equation if you wish, right? And Garrett did it in his head. But you can always, if you can't do it in your head, negative b plus or minus the square root of b squared minus 4ac all over 2a. So I have -2 and -1, right? Those are the actual poles of my system. And when I put them and represent them in here, I have s plus 1 times s plus 2. So those are our poles. They live in the left-hand half plane. We have a stable system. So our step response, if we energize this with a step response, again, looking back at the homework, one of the suggested problems, we're going to have something that goes like this. Here's our A, here's our C of t, A plus B1 e to the minus 2t plus B2 e to the minus 2t. This right here doesn't go to infinity. And these both have exponential decay. By the way, which is going to be the faster to decay pole? B1 or B2? Everybody agree? Let's check. Remember, it takes 5 time constants. So e to the minus t over tau for the B1 case is going to be e to the minus t over 1. For the B2 case, is 1 divided by 1 equal 1? Is 1 divided by 0.5 equal to 2? Is that equal to? Okay, so 5 time constants. Anybody want to change their vote?
The equivalent wall, the look at the.
That was a question, which is which one decays faster? And you all said this one. That's correct. That's what that said. But when I asked the question, I said, which one decays first? You said this one. So this one doesn't decay first. This decays in 5 seconds. This one is 2.5 seconds. So the further you are over here, the faster it decays. Wasn't meant to be a trick question, right? Just go back to our e to the minus t over tau. That's why we keep bringing some of these things back up. Okay, so it actually reaches steady state based on that one, right? That's the slowest one, so we have to decay it, but it's still a stable system. All right, party people, let's see if Garrett, let's cheer him on. Can Garrett do this one now? No. No, you can't tell. Unless you use your calculator or MATLAB, right? You can do it in your calculator or MATLAB, and you can go ahead and solve that. So here is what it's factored. Is it a stable system? Why is it not stable? Which pole is in the right-hand half plane? Yeah, because when I plug in S equals +3, then I have a pole in the right-hand half plane. So that's the bad one. And if you look over here, here's my pole 0 map. Remember the rule about system stability? For a system to be stable, all poles must be in the left-hand half plane. I have one pole in the right-hand half plane. So not Bible stable. Here's my step response when I do partial fraction expansion. And take a look. This is not decaying exponentially. This is increasing, is it not? Because e to the +3t, if I did this here, it takes 5 time constants to get stable, right? How long does that take? Negative 1.33 seconds. How can you have negative 1.33 seconds? So this work here is not valid. When you have non-decaying exponential systems, you can't use 5 tau for it to reach exponential decay because you would go back in time. It doesn't work that way. You only move forward in time. So this is a system that we can see as time increases, it never decays away. Its output is increasing and increasing and increasing until the system breaks or you run out of steam. How about this one? Stable? Is it Bible stable? No calculators or MATLAB, please. We have one yes. And
No, on the zero, so it's S plus zero.
S plus 0,
So it's S plus zero, right, it's three, which means on the zero, even, yeah. You know, which means on the thing.
if we wrote that in standard form, that is my real part of my pole. Is that in the left-hand half plane? It's on the j omega axis. And the rule we say about j omega axis is what? What's the stability rule we have? It's a marginally stable system, which means it's not Bible stable because I can bound my input, right? I can bound it with something, but I could still get a system that increases exponentially. So this is a marginally stable system. I don't know if it's going to be a stable output. So here's how we break it all the way down. We have two poles on the j omega axis. That's why it's nice to draw pole zero maps, because you can really, it screams at you when you do it that way. And then our step response, we can see this is a unit step, and it looks pretty good, right? That is bounded. When you provide it with a unit step input, it's bounded. So that's why it's a marginally stable system, because the output could be stable. But if we excite it at its natural frequency, sine of 3t, now we do it, we end up with s squared plus 3 squared, so over under some coefficient. Then we have an s squared plus 3 squared squared, again over some coefficient. And now what we end up with in our time domain is this one is okay. This one is not okay. Because as time increases, t keeps getting bigger and bigger and bigger. So my sine wave starts going until it runs off the screen. We can't get there from here. So this is an unstable system. Well, the system is marginally stable, but the output is unstable if we excite it at its natural frequency. So LTI, linear time invariant system, is Bibo stable if all poles are in the left-hand half plane. Anything beyond a second order system can be painful. What I mean by painful is you have to use MATLAB or a calculator, so maybe not super painful. And we're going to pause here because to really introduce the Routh-Hurwitz plot, the Routh-Hurwitz approach, we have to do a lot of math. You can see if I show you the whole process. Usually like to get there from here, so I don't think I have enough time to get into it. So we'll pick up by considering this. The only thing we need to focus on is we've got some coefficients here, A2, A1, A0, that are going to be determined by expanding out that third order pole. So any questions from TV land? But it's, you know the homework stuff, and we went through that a little bit at the beginning of class. You've got homework. We did it kind of in the middle of class as well. The homework that's due Thursday, that's going well. That's not a very confident yes.
I glanced at it.
Okay. How about TV land? Any issues with any of the homework thus far?
Not yet.
Okay. All right, well, if there's no other questions, have a great day all, and I will see you on Thursday. Take care, everyone.
Thank you, Paul.
Thank you.